Okay, let's unpack this. Have you ever stopped to think about the air around you? I mean, really think about it, not just as, something to breathe, but as a tangible, powerful force. Today, we're diving into our first episode of the PIAB podcast, The Power of Nothing. And our mission really is to pull out the most important nuggets of knowledge for you, sort of shortcut your way to being well-informed, get ready for some aha moments.
Yeah, it's fascinating, isn't it? How something so fundamental, so invisible, really shapes our world and enables some incredible technology. We're going to try and connect the dots for you, between the air you're breathing right now and the sophisticated applications of, nothingness.
Nothingness. I like that. Okay, so let's kick off with something pretty surprising. You, right now, listening to this, you're living at the bottom of a deep ocean. An ocean of air. It extends for kilometers above us.
That's exactly right. It's not just a neat idea. It's a massive layer of gas. And gravity pulls on this huge blanket of air. And that pull, well, that's what creates atmospheric pressure. It's naturally greatest right here at the Earth's surface, down in the deep end, you could say.
Right, the deep end of the air ocean. And pressure is force per unit area, right?
Correct. Force over area.
So the numbers. At sea level, it's about 14.7 psi, or 101.3 kilopascals for metric folks. But here's the mind-blowing bit. Imagine a small kitchen table, just 1 square meter. The force pushing down on just that table from the air is, get this, around 101,000 newtons.
Which is huge.
Yeah, that's like the weight of 10 cars sitting on your kitchen table.
It sounds completely wild when you put it like that. 10 cars. And this raises an important question. If that much force is on you and on your table, why aren't we crushed? Why doesn't the table just, splinter into pieces?
Exactly. That's the first thing I thought. 10 cars. How is anything still standing?
Well, the crucial thing to understand here, the key principle, is that pressure in a fluid, and air is a fluid, it transmits in all directions, not just down.
Ah, okay. Not just downwards.
Right. So those 101,000 newtons pushing down on the table, they're balanced, perfectly balanced by an equal force pushing up from underneath. Same goes for us. Our bodies aren't crushed because the fluids inside us, in our cells, our blood, they exert an outward pressure that balances the atmosphere pushing in. It's equilibrium.
So it's a constant balancing act. Pressure pushing in, pressure pushing out. Okay, that makes more sense than 10 invisible cars. This reminds me of that classic demo, the water and card trick.
Oh, yeah, that's a great one.
You fill a glass with water, slap a card on top, flip it over, and the water stays in. How does that work with this pressure idea?
It's a fantastic illustration, actually. So the air pressure outside the glass is pushing up on that card. Inside, at the top, above the water, you basically got a little vacuum, or very low pressure anyway. There's hardly any air pushing down on the water from inside. So the only real downward force is just the weight of the water itself. And that upward push from the atmosphere on the card is easily strong enough to hold the water's way up.
Wow. And the force is pretty significant, even on a small glass opening.
Oh, absolutely. For a typical drinking glass, maybe, 6 centimeters across, that upward force is something like 286 newtons.
286 newtons. That's 64 pounds pushing up on that little card.
Exactly. Way more than needed to hold a glass of water. And think about this. If you poked a hole in the top of the glass, what happens?
The water would fall out.
Right. Because air would rush in through the hole, and suddenly you'd have atmospheric pressure pushing down on the water from inside, balancing the pressure outside. Gravity then takes over. It's the lack of downward air pressure inside that makes the trick work.
Got it. So this pressure isn't just some abstract thing. It's vital. We couldn't live without it.
Absolutely not. It's fundamental. Take breathing, for instance. Your body uses air pressure constantly. Your diaphragm contracts, your chest expands. That lowers the pressure inside your lungs.
Lower than the outside air.
Right. So the higher pressure air outside naturally flows in. Then your diaphragm relaxes, chest volume decreases, pressure goes up inside.
And the air gets pushed out. Wow. Simple mechanism, but totally reliant on that outside pressure.
Couldn't happen without it.
And it's not just breathing, right? You mentioned other things. Pumps, syringes, drinking straws.
Yeah, drinking straws are a great example of a common misunderstanding. You think you're sucking the liquid up, don't you?
Well, yeah, that's what it feels like.
But you're not, really. What you're doing is removing air from inside the straw. That lowers the pressure inside the straw. The atmospheric pressure outside, pressing down on the surface of your drink, stays the same. And it's higher. So that higher outside pressure actually pushes the liquid up the straw into your mouth.
Ah, so it's the atmosphere doing the work again. Pushing, not sucking. That changes how you think about it. Okay, so This powerful, invisible force is all around us doing all this work. How does this let us create the opposite? How do we make a vacuum?
Well, defining vacuum first helps. Generally, it's a space empty of matter. But practically speaking, especially in industry, it's just a region where the gas pressure is much lower than the surrounding atmospheric pressure.
Lower than the air around it.
Exactly. A volume reading, a lower pressure. And here's the key connection. It's that very atmospheric pressure, that strong force we've been talking about, that actually allows us to create and maintain these low pressure zones, these vacuums.
Right, you use the existing pressure to sort of carve out a space of lower pressure, like with a suction cup. That seems like a perfect example. How does that stick?
It really is a perfect everyday example. When you press a suction cup onto a surface, you push most of the air out from underneath.
Squishing the air out.
Yep. That dramatically lowers the pressure inside the cup.
Right.
But the pressure outside the cup, good old atmospheric pressure, hasn't changed. So you've got high pressure outside, low pressure inside. That pressure difference means the atmosphere is pushing the cup firmly against the surface.
Pushing it on, creating the seal.
Exactly. It's not the cup pulling, it's the atmosphere pushing. Always pushing.
This pushing idea is really sticking now. Okay, so this force, this atmospheric pressure, is it the same everywhere? We talked about sea level. What if you go up a mountain?
Good question. Altitude matters a lot. As you go higher, that ocean of air above you gets shallower. There's simply less air piled on top of you.
Makes sense. Less air, less weight.
Less weight, less pressure. So atmospheric pressure decreases as your altitude increases.
Which is why things feel different in, say, Denver or Mexico City. They're quite high up.
Exactly. The air is thinner, pressure is lower. It affects everything from boiling points to, well, how well suction cups work.
How much lower can it get? Like Mount Everest high?
Dramatically lower. At the summit of Everest, was it 8,848 meters?
Something like that, yeah.
The pressure is only about 33 kilopascals. That's roughly 1/3 of the pressure at sea level.
1/3. So if my suction cup could lift, say, 10 kilos at the beach.
On top of Everest, same cup, same pump. It could only lift about 3 kilos.
Wow, that's a huge difference.
It really highlights how much that atmospheric push contributes. Less push available at altitude means less lifting force.
Okay, so the big takeaway there is location, location, location matters for pressure. Your altitude directly impacts anything relying on this force. So if we're dealing with these different pressures, how do we actually, talk about vacuum, measure it? Are there different scales or units?
First, there's the scale. Are you measuring absolute pressure, which is relative to a perfect vacuum, zero pressure, or are you measuring gauge pressure, which is relative to whatever the current atmospheric pressure happens to be, which, remember, changes with weather and altitude?
Right, so you need to know your starting point, zero, or the air around you.
Precisely. And then there are the units. You've got pascals, PSI. Those are common. But for vacuum, you often see negative values used for gauge pressure, like negative kilopascals. PIAB uses this a lot. It's quite intuitive.
Yeah, so?
Well, with negative kilopascal, a bigger negative number means a deeper vacuum. So negative 80 kilopascal is a stronger vacuum than negative 60 kilopascal. They're related to percentages too, where 100% vacuum is about negative 101.3 kilopascal full atmosphere pressure difference.
Okay, yeah. I can see how negative kPa makes it clearer. More negative means more suck, or rather more potential push from the outside.
Exactly. You'll also see inches of mercury, especially in the US, and scientists might use torr or millibars. Lots of ways to say the same thing.
So different languages for pressure. And are there different types or ranges of vacuum? Like, is the vacuum in my vacuum cleaner the same as in a science lab?
Definitely not. We categorize them. There's low vacuum, maybe 0 to negative 20 kPa. That's your ventilation, your Hoover. Then there's the broad range called industrial vacuum. That's kind of the sweet spot covering most manufacturing and handling tasks. And then you get into high vacuum. That's like negative 99 kPa and beyond. Really, really low pressures.
And what needs that kind of vacuum?
Very specialized stuff. Manufacturing computer chips, coating lenses, metal vaporization processes, things that need an extremely clean, near-empty environment.
Okay, that makes sense. Different jobs need different levels of nothingness. Now, there's a fundamental physics law here, too, isn't there? Boyle's law. How does that fit in?
Boyle's law. Absolutely fundamental for gases. It basically says P times V equals a constant.
Pressure times volume is constant.
Right. For a fixed amount of gas at a constant temperature. So if you increase the pressure on a gas, its volume has to decrease to keep that product constant.
Like squeezing that balloon again. More pressure, less volume.
Exactly. And if you decrease the pressure, the volume expands. It's the inverse relationship.
Okay, simple enough. But what does that mean for actually making a vacuum? Does it relate to the effort involved?
It does, significantly. It ties into the energy needed.
Mhm.
Because of this relationship and other gas behaviors, achieving deeper vacuum levels gets exponentially harder. Think about pumping air out of a container. Removing the first 90% of the air is relatively easy.
Yeah, lots of molecules to grab.
Right. But removing 90% of what's left, that's much harder. And the next 90%, even harder. There are fewer molecules, and they're harder to catch, essentially. So reaching, say, 9 to 99 kPa might require pumping out a conceptual volume of 10 meters of air equivalent, but getting to 90 to 99.9 kPa, that might take over 100 meters equivalent. The energy and time cost shoots way up.
Wow. So diminishing returns. Big time.
Hugely, which leads to some practical advice for you, the learner. For most industrial jobs, trying to achieve a vacuum much deeper than 60% to 70%, which is about -60 to -70 kPa gauge, usually isn't worth the additional energy and time it requires.
Find the right level for the job. Don't just aim for the deepest possible vacuum unless you absolutely need it.
Precisely. Optimize for efficiency.
That's really useful advice. So the machines that do this, the vacuum pumps, they have to deal with this, right? How do they work?
Well, vacuum pumps have two main characteristics you look at. First, the vacuum level they can achieve, how deep they can go pressure-wise. Second, their vacuum flow, how much air volume they can actually move per unit of time, how fast they can suck the air out.
Okay, level and flow, are they related?
They are, and it's usually an inverse relationship tied back to what we just discussed. When the vacuum level is low, closer to atmospheric pressure, the pump can typically achieve high flow because there's lots of air to move easily. But as the pump works and the vacuum level gets deeper, pressure gets lower, the flow rate tends to decrease. There are just fewer air molecules left inside to pump out.
So a pump might be good at reaching a deep vacuum but slow at it, or fast at removing bulk air but maybe not reaching super low pressures?
Exactly. Different pump designs are optimized for different things. Some prioritize deep vacuum levels, others prioritize high flow rates. And then you have things like multi-stage pumps that try to combine these characteristics, offering a balance for more general-purpose applications.
It's always a trade-off, it seems. Okay, so we understand the pressure, the vacuum, the physics. What can we actually do with all this, beyond suction cups and breathing?
Oh, the applications are incredibly diverse. We've mentioned lifting, picking, handling, holding things. That's huge in automation and robotics. But vacuum is also critical in conveying systems, moving powders, grains, liquids, sorting items. Vacuum can transport materials cleanly and efficiently.
Like those pneumatic tubes at the bank, but on an industrial scale.
Sort of, yeah. And then there are process applications, using vacuum for things like filtration, where the pressure difference pulls liquid through a filter, or evaporation and degassing, removing dissolved gases from liquid. Remember how lower pressure lowers the boiling point?
And you mentioned that with altitude.
Well, you can use vacuum to make liquids boil or evaporate at much lower temperatures than normal, which is really useful for delicate substances in food processing or chemical engineering.
So it's not just about holding things, it's about moving things, separating things, changing the state of things. It's incredibly versatile.
It really is. It's one of those foundational technologies that enables so much, often behind the scenes.
Absolutely. Okay, let's try and sum this up. We started with this idea of an invisible ocean of air.
Weighing down with a force of 10 cars.
Right, but balanced, so we're not crushed. We saw how that pressure lets us do the card trick, how it's essential for breathing, how it makes straws work.
By pushing, not sucking.
By pushing. And then how we use that atmospheric push to create its opposite vacuum, measured in various ways, governed by Boyle's law.
And understanding the deeper vacuum costs exponentially more energy,
leading to all sorts of applications, from simple suction cups and pumps right through to complex industrial processes like conveying and degassing.
It's a journey from the air around us to high-tech manufacturing.
Definitely. So here's a final thought to leave you with, building on all this.
Knowing how much energy it really takes to create that perfect vacuum, that near nothingness, and knowing how much immense free power is available in the everyday atmosphere constantly pushing down, this raises an important question. What new problems could you solve if you started looking at the air around you not just as empty space, but as this infinite, powerful, and crucially free resource?
That is a great question to ponder. What could you do with the power of nothing and everything around it?
We really hope this first episode has given you a fresh perspective, maybe some surprising insights into vacuum theory. Keep exploring, keep questioning, and we'll see you on the next episode here in the PIAB podcast.